Hello friends. So today we are going to start our brand new series on class 11's mathematics, mainly focused on CBSE. So mostly we will be in line with what NCERT teaches, with slight deviation here and there. So the first topic we are going to start would be sets. So we can define a set. Set is a well-defined collection of objects. So if a collection of object is well defined, then we can say that it comes under the category of sets. For example, if I say uh, all the vowels of English alphabets. So everyone will answer the same thing. Like if I ask to you, you will say it's A, E, I, O, and U. So it's always the same. It doesn't matter whom I ask. So it's a well defined collection. So we can say that it's a set. Another example could be all the factors of 10. So what are the factors of 10? It would be 1, 2, 5, and 10. So it's also well defined. So it's we can also say that it's a set. But if we see some uh, other examples, like if I ask someone a collection of top 10 most talented people in India, so clearly it's not well defined. So we can say that it's not a set. So whereas this comes under set, this is also set. This is not a set because we cannot define. This answer will vary from person to person. And if we ask 10 different people, we will get 10 different answers. So this will not be a set, but these two will be set. So now moving forward, uh, sets are usually defined by capital letters. Like here, we have defined the set of vowels. So we can say that we can denote it like this: capital V, and then write equal to. And so there are a couple of rules. First, I said that usually we define set by capital letters. Then we include the elements of the set in curly braces. So this would be the correct way of defining a set. So first rule was capital letters, and the second rule was elements, or we can say members, or we can also say objects. All are same. So objects of set are enclosed within curly braces. So this was our second rule. So now we will come to more terminology. Uh, so here V is the set, right? And these are the elements, members or objects, whatever you like, you can say it. So A is a member of V. E is also a member of V. I is also a member of V. Similarly, O and U. So uh, we can write it as A is sorry small a is a member of set V. This is equivalent to saying A belongs to V. Both are same, and in notation we will write it as A, and we have a symbol like this which denotes belongs to. So we can also write it as V. So all three are same things. All three are basically different ways of saying things. So this belongs to, we denote it using this symbol, special symbol. So next time you see something written like this, it means A belongs to V. So A is an element of set V. Similarly, here V is the set of all vowels. So it has only 5 elements, and B is not a member of. So B is not a member of V because V is a set of all vowels only, not consonants, and B is a consonant. So in other words, we will write it as B does not belong to V, and we will write B V, and we have a different symbol here. It's the same as early, but this time we do a cross mark. So this means belongs to, and this symbol means does not belong to. So now let's look at some more examples of set, and we will look at some well-defined examples of set which we study especially in mathematics. So first we will see uh, natural numbers. So in mathematics we denote it using a special symbol capital N. So this is the symbol for natural numbers. And what are the examples of natural numbers? So all the numbers we use for counting, like 1, 2, 3, 4, 5, and so on. It starts from 1. So this was our first example. So next would be whole numbers. So whole numbers are same as natural numbers, but it starts from 0. 0, 1, 2, 3, 4, and so on. So the only difference between natural numbers and whole numbers is that 0 is included in whole numbers. Our third example would be integers, and this also has a well-defined symbol which we usually denote integers using capital Z, or sometimes you will see I also, but capital G is more prominently used. And the integers would be natural whole numbers and then negative natural numbers. So you can say that it starts from negative infinity, then -3, -2, -1, 0, 1, 2, 3, and so on. So it extends from minus infinity till plus infinity. So next we can see uh, positive integers. So this is the same as integers, only difference is that we will exclude the negative terms and we will denote it using z plus. So positive integers would be this part of the integers. We will ignore all the negative parts. Okay, let's move to our next example. So rational numbers, and we usually define it using capital Q. And its definition is that rational numbers are the numbers which can be denoted in the form p by q, that is ratio of two numbers, where q should never be equal to 0, because if q is 0 we cannot define number. For example, we write 5 divided by 0. So we do the mathematics. So 5, so we have to find what number should I multiply to 0 so that I get 5. So if I see, if we take any numbers, say take the largest number 9. So 9 times, 0 should be here, and 0 and 5. We take the largest single digit number 9, multiply by 0, we get 0. Again remainder is 5. Again multiply by 9. Again 0. Again we subtract is 5, and this will go on. So any number, any value you can think of, if we multiply by 0, we get 0 only. So we will never reach at some answer for this. So it would not be defined. So any number which can be represented as p by q form, and q is not equal to 0, then that will come under the category of rational numbers. So we can take some examples like 2 by 3, 10 by 5. So is 5 a rational number or not? Yes, it's a rational number, though although explicitly we have not written in p by q form, but we can always write 5 is equal to 5 upon 1. Any number can be written as that number divided by 1. So 5 is also a rational number. Now we will see our next example, irrational numbers. So rational numbers could be represented in some p by q form, but irrational numbers we cannot represent using p by q. So we can see some example for, like, most common example would be pi. So pi, the value of pi is 3.14159 and so on. So the value will continue, it will never terminate. So for rational numbers, either we get some fixed answer, like for 10 by 5 we get 2, 5 by 1 we get 5. For 2 by 3 it's not perfectly divisible, but we will get some fixed value like 0.666. It will continue, recurring number. So we are not getting every time a new number. Or like 13 by 7, what would be 1.8571. So let's divide 7 6 and then 60, 8 times 56, then 4 is remainder, 5 times 35, then 50, 7 times 49, then 1, then 4, 28, 2 is remaining, then 2, now we have 6, so 60, again 8, so it will keep repeating. 7, 1, so let me separate it so that you see the repeating pattern, so it will keep repeating. So we will write it as 1.85714 and then bar over it, so this number is repeating again and again, sorry, till here. So this number will keep repeating, so it terminates basically. It's non-terminating, but we get some pattern here, or like 10 over 8, so it will be 2.5, so it terminates perfectly. So either it terminates or we get some pattern which repeats itself. So these all are rational numbers, but irrational numbers are those numbers which never terminate, or we don't get any fixed pattern or repetition of decimal digits. So for example, pi never terminates, and we also don't get some fixed repeating pattern. Similarly, all the numbers root 2, so which are not perfect square roots. For example, root 25 we get a perfect answer. These are perfect squares, but for non-perfect square numbers, these values will never terminate, or we will not get any fixed repeating set of patterns. So these all come under irrational numbers. So next example we would see is real numbers, and we have a symbol for this. So we denote real numbers by capital R, and same as integers, like we denote integers using Z and positive integers using Z plus. We denote positive real numbers using R plus, negative real numbers using R minus, and same here, negative integers using Z minus. So now what are real numbers? So we have seen rational numbers, we have seen irrational numbers. So real numbers would be all the numbers including rational and irrational numbers plus irrational numbers. So these all come under real numbers. Now we will look into some more terminology. So with sets we define a term called cardinality of a set. So in earlier example we had seen that V is equal to A, E, I, O, U. So this was the set of all the vowels in English alphabet. So how many elements are there in set V? So we see that there are 5 elements: A, E, I, O and U. So we will say that the cardinality of set V is equal to 5, and we will denote it as, small n is equal to 5. So cardinality is simply the number of elements inside a set. Now we will see what are the different ways we can represent a set. So here we have been representing in this form, the set with capital letter and the elements of set separated by comma inside curly braces. So this was one of the ways of representing set. We have other ways of representing the set also. So mainly we have two ways to represent a set. So the first is called roster method, or it's also called tabular method. It's the same one we have been looking here. So in this method, we all the elements of the set are separated by comma inside the curly braces. So its example would be this. The other method is called set builder form, and in tabular method we actually write down the entire set, all the elements of the set we write, and these are separated by comma. In set builder, we will convey the same information but in slightly different way. We will write it as x such that x is a vowel of English alphabet. So here we are actually writing the elements. Here we are writing the property that is common to all the elements. So here we will write actual elements of set, and here we will write property common to all elements of set. So this is the main difference. Here we are writing actual elements, here we are writing the common property. So if we write and we read this symbol as such that, so here also we are denoting it using capital letters and the elements inside the curly braces, but here we are writing the property which is common to all elements. So V is a set of elements x such that x is a vowel of English alphabet. So we are telling the property. We are telling the property of the elements. So this is the main difference. So these are the two main ways to represent a set. So till now we have been looking at sets which had some elements inside them, but we can have a set for which there is no element inside that. So we will call those types of set as empty sets. So we will see some example, like we define A is a set which is set of all the Indian states which are outside Asia. So we have defined the set, we have defined the property of elements of the set. So if we define A as the set of all Indian states which are in India, then clearly we will have 28 values into it, like uh, Karnataka, Andhra, Madhya Pradesh, and so on. So we will have a well-defined set. But if we define the property as set of all Indian states which are outside Asia, India is in Asia, and Indian states also has to be inside India only. So if we define it in such way, then clearly we don't have any answer for this, and there will be no element in the set. So we will define it as just curly braces and no element inside it. So our empty sets are denoted by this empty curly braces or phi. So both are same things. So we will denote empty sets using these, and this simply means that there is no element in that set. So another example, can be like B. B is a set of X. I am writing it in set builder form, you see. So B is a set of elements X such that X is greater than 7 and X is less than 11 and X is prime. So 7 is a prime, but X should be greater than 7. So greater than 7 and less than 11. So 8 is not a prime. 9 is not a prime. 10 is not a prime. So say X is either 8, 9 or 10 and it should be prime. So clearly it does, we cannot find any element which satisfies this property. So this is again an empty set. So now we will look into some more definitions. So we will look as finite and infinite sets. So first let's see finite sets. So I will copy the value from here. So earlier we had defined a set of all the vowels, and so we had defined its cardinality or the number of elements inside the set. It has 5 elements. But now take this example, the example of integers or whole numbers, or any example we can take. So we cannot count the number of elements inside this. So whereas this set had 5 elements, this set we cannot count, it has infinite number of elements. So as the name suggests, the sets which have finite number of elements, those are finite sets. The sets which have infinite number of elements, those are infinite sets. So similarly, the set of all the whole numbers, this is also infinite. This is also infinite. Whereas this is finite, this is finite. All these are finite sets. So I hope this is clear. This is pretty simple. Uh, Now we will look into some more definitions. Equal sets. So suppose we have a set A which is 1, 2, 3, 4, and we have another set B which is 4, 2, 1, 3. So and we have another set C which is 2, 3, 4, 5 and 6. So if we compare A and B, we see that 1 is present here, 1 is also present here, 2 is present here, 2 is also present here, 3 is present here, 3 is also present here, 4 is present, 4 is present. So all the elements of A are present in B and all the elements of B are also present in A. So basically A and B both have the same number of elements as well as the same elements. Whereas if we compare, look into C here, 1 is here but 1 is not present here in the C. Whereas 5 and 6 are present in C but it's not present in A. So first case we will say that A and B both have same elements. So A is equal to B and we will say that A and B are equal sets. Sets A and B are equal to each other, or A and B are equal sets. Whereas A and C are not equal sets because all the elements in A are not present in C and vice versa. Similarly, B is also not equal to C. So we see that the order in which elements are written is not important. We can write it in any order. So we see that order of elements is not important. And second, we generally write an element only single time. Uh, so we will not write 4 to 1 3 and 3 again. So uh, write elements once. So these points should be kept in mind. So the order of elements is not relevant, and we usually write the elements only one time. So that's why A and B are same or equal, because they are consisting of the same elements and same number of elements. So we will dive into more terminology, and we will look into what are subsets. So till now we have been looking into sets. Now we will see what are subsets. So a set A is said to be a subset of set B if every element of A is also an element of B. So let's we have A, which is 1 2 3 4 and 5, and we have an element B. We have a set B which has 2 4 and 3. So here B has 2 which is present in A, 4 which is present in A, 3 which is also present in A. So all elements of set B are present in A, but all elements of A are not present in B. So we will write it as B is a subset of A. So this symbol here means it is read as is a subset of. So we will read it as B is a subset of A, or equivalently we will write A is a superset of B. So notice the symbol here, it's these two are kind of mirror images. So we write it this way and this other way. So B is a subset of A, or A is a superset of B. Both are same things. But A is not a subset of B, because all the elements of A are not present in B. So we will write it as this. So we have another symbol here. It means is not a subset of. So I will write it here. Is not a subset of. But if we have another set, say, which is also 2 3 4 5 and 1, so we see that A and C are basically equal sets. So all elements here are present in A, and all elements in A are also present in C. So it's not necessary that B should be a proper subset of A, but even if they are equal, we can say that C is a subset of A. But in this case, and A is also a subset of C. So if both these cases are satisfied, that is C is a subset of A and A is a subset of C, then we can say that these two are equal. A is equal to C. So every set is a subset of itself also, and it's also a superset of itself. So this is always true. So now we will look into another term called power sets. So what are power sets? So till now we have been looking into single sets. So A is a set of 1, 2, 3, 4, 5, B is a set of this, V is a set of all the vowels. So suppose A is a set of 1, 2 and 3, and we had just now studied what are subsets. Subset is if we pick some elements or all of a set and create a new collection, we get a subset. So we have to pick some or all of the elements. We will get a new collection or new set, and that set is called subset of the bigger set. So what can be the subsets of A? So one thing could be we picked everything and we get a set 1 to 3. So this is a subset of this. And next time suppose I drop 3. So 1, 2. Next time I drop 2. I get 1, 3. Next time I suppose drop 1. Then I get 2, 3. Now I drop 2 and 3. I get 1. Now I just pick 2. I can also just pick 3. And I can drop everything. So these are the possible subsets. These are subsets of A. 1, 2, 3, 4, 5, 6, 7 and 8. These are the subsets of A. Now suppose I create a set P of A whose elements are all the subsets of A. So I will copy this and paste it here. So this PA is a set whose elements are the subsets of A. So PA is a set of sets, set of subsets of A. So we will call it as PA and we will read it as power set of A. So this will be read as power set of A is equal to P of A is equal to this value. So the power set of any set is the set of all the subsets of the original set. And how many sets we can create? If it has say k elements, then the number of subsets would be 2 to the power k. For example, here we have 3 elements. So number of subsets would be 2 to the power 3, which is 8. So if cardinality, remember the term NA to denote cardinality. If NA is equal to K, then N of power set of A is equal to 2 raised to the power K. And how this number comes? So if we have 3 numbers, so we have 3 numbers. So first number either we pick it or we don't pick it in the set, in the subset that we create. So there are two ways select this, either we select it or not. Second, also we have two ways, either we select it or not. Third, also two ways, either we select it or not. So total there would be eight possible ways to select these. So if there are k elements, so for each k element either we select that kth element or not. So we will have 2 raised to the power k elements in the power set or number. If you are asked a set has 10 elements, how many subsets of that set are possible, then you will say 2 raised to the power 10. So the last topic that we'll see in this introductory lecture would be another terminology which we will call universal set. And so suppose in some context we have a number of sets like A is a set of all prime numbers, right? And let's suppose B is set of all even numbers. C is a set of odd numbers. So here we have a context, and this context we are talking about three sets, A, B and C. A is a set of all prime numbers, B is a set of all even numbers. So what are prime numbers? 2, 3, 5, 7, 11. Any number which is divisible by itself and 1. So 3 is also divisible by 1 and 3. 5 is also divisible by 1 and 5. So 2, 3, 5, 7, 11 and so on. This is the set of prime numbers. And even numbers, we can write 0, 2, 4 and so on. Odd numbers we will write 1, 3, 5 and so on. So here we are talking about only three sets, these three sets. Suppose we remember that earlier we had defined whole numbers. Suppose I denote by W, or let's say integers. What are integers? Integers are minus infinity and then 2, minus 2, minus 1, 0, 1, 2, 3 and so on. So if we see that integer ranges from minus infinity to plus infinity, so is set A contained inside this Z? Yes. 2 is here, 3 is here, 5 is here. So we will say that A is a subset of Z. Similarly, B is a set of even number 0, 2, 4, 6, 8. This is also contained inside this Z. So we will write B is a subset of Z. Then we look at C. C is 1, 3, 5, 7, so on. So 1, 3, 5, 7. So this is also contained inside Z. So we will write C is a subset of Z. So we see that Z includes all the elements present in all the sets. Here three sets. So we will say that Z is a universal set of A, B and C, and we usually denote it by capital U. So we can write as capital U of A, B, C is equal to Z. So here capital Z is the universal set for A, B and C, because all the elements because Z includes all the elements that are present in A, B, and C. So with that we will end today's lecture, and in the next lecture we will see about some operations that we can perform on sets. So in this lecture we were only focusing on mainly the terminology associated with the sets. In the next lecture we will see the ways to represent set on Venn diagram, and we will see some operations, that complex operations that we can perform on these sets. So thanks.